Hello pre-calculus students. We're going to work together today on Module 3 Investigation 2, Function Relations and Domain of Functions. First, we really need to read all this stuff at the top of the screen. Oftentimes, the key to solving all your problems are just going to be these definitions. So, in the previous investigation, you related values of two quantities by writing formulas to describe how values of one quantity are related to values of another quantity. If the two quantities are related in such a way that each input to the formula generates exactly one output value, we can say that the formula defines a function. So that's a key sentence. A function consists of three parts: a set of input values referred to as the domain of the function, a set of output values referred to as the range of the function, a rule that assigns to each input value exactly one output value. It is also common to say that a function relates values of the independent variable to values of the function's dependent or output variable. And there's some stuff about terminology here. We say P is a function of S, meaning P represents the output and S represents the input. We say P in terms of S for basically the same thing, and we say P with respect to S again, meaning P represents the output and S represents the input. First, number 1, recall the box problem from Module 3 Investigation 1. Consider the volume of the box in terms of the length of the side of the square cutout. What is the input quantity? This question is pretty straightforward. We just need to use our definition of a function. Notice that we have considered the volume of the box in terms of the length of the side of the square cutout. And remember that when we say in terms of, the last thing we refer to represents the input. If we want the volume of the box in terms of the length of the side of the square cutout, then the input quantity is the length of the square cutout. We need to be a little bit more precise here. It's really not just the length of the square cutout, but the length of the side of the square cutout. Now for the output quantity, that's simply the volume. The volume of the resulting box. Now the next question asks, is the relationship a function? Explain. All we got to do here is think about what it means to be a function. Remember that sentence that I pointed out was pretty important. If two quantities are related in such a way that each input to the formula generates exactly one output, and there's the key words there, the exactly one output value, we can say that the formula defines a function. And that's, again, in number 3 here, a rule that assigns to each input value exactly one output value. So if you think about the length of the side of the square cutout, we can't cut out a square from 4 sides of our piece of paper and fold up and make the box and get 2 different volumes. The length of the square cutout determines what the volume will be. So for each input value, there's exactly one output value. For each length of the square cutout, there's only going to be one corresponding function value. So our answer is yes. Okay, moving on to part B. Consider the length of this square cutout in terms of the volume of the box. In this case, the input quantity is the volume of the box, because we've stated that it's in terms of the volume of the box. So that's the input quantity. The output quantity is the length of the side of the square cutout. And is the relationship a function? So you guys might recall from class where there were two different cutout lengths in which that gave us the same volume. I think it was maybe like a half an inch gave us a volume of, I don't know, maybe 37.5 inches cubed, and then there was another measurement, it was perhaps 3 inches, that gave us the same volume measurement of 37.5 inches cubed. And so for each volume input, if we make volume the input, then if we pick 37.5 inches cubed, what are we going to assign to the output? There's not only one value to assign. This goes back to the definition. So this one's not a function. If we look back here, a rule that assigns to each input value exactly one output value, number 3 up here. So this relationship is not a function because for some values of the input quantity, which is volume in this case, there are more than one possible values for the output quantity, length of the side of the square cutout. Number 2. Consider the percentage grade on a test in terms of the letter grade earned. What is the input quantity? Here we want the percentage grade in terms of the letter grade earned. So the letter grade earned is the input quantity. What is the output quantity? It is the percentage grade on a test. So again, if this is confusing, just go back to the definition. That's all we need to think about. Is the relationship a function? So we have to think, for any particular letter grade earned, is there exactly one percentage grade on a test that goes along with it? So say, for example, let's say that in our class, the input, like let's say for the last test, let's say, so we're going to have, let's see, consider test 1. Let's let the input be a B, just the letter grade B. So if I go back and I look through all the tests, a lot of students made B's. So which would be the output quantity? Is there a particular output quantity I can assign? Does B determine which what is going to be my output quantity? The answer is no. There are many possible values for the output. Somebody made an 81 on the test, another student made an 83, somebody made an 89. And if we again just go back to the definition of a function, at the top of the page here, a function is a rule that assigns to each input value exactly one output value. And with the test, for each input value, A, B, C, D, or F, there are many possible output values. So this is not a function. The relationship is not a function because for any input value, which is the grades, there is not exactly one output value. Numeric grades, percentage grades. Now question 3 just reverses basically the quantities in the last question. Consider the letter grade earned in terms of the percentage grade earned. Here, Letter grades are in terms of the percentage grade, so the input quantity is the percentage grade earned. The output quantity is the letter grade. And is the relationship a function? This time the answer is yes. The relationship is a function because for any input value, which is a percentage grade, there is exactly one corresponding output value, which will be the letter grade. If you give me any percentage grade, 81, that's our input, the output is a B. 83, the output is a B. 86, the output is a B. There's exactly one output for each input. This is different from the last problem in which we picked a letter grade first and as our input, then there's all sorts of different possible outputs. So the order of your quantities really makes a difference when you're thinking about functions. Question number 4. The following table shows the average monthly rainfall in inches per month, R, in Phoenix, given the number of months since January 1st, T. Consider the average monthly rainfall with respect to the number of months since January 1st. What is the input quantity? The input quantity is the number of months since January 1st. Notice that we say the average monthly rainfall with respect to the number of months since January 1st. That with respect to whatever comes after that, that's the input quantity, or the independent variable. The output quantity is the average monthly rainfall. Notice that we're talking about average rainfall, meaning we take like the amount of rain, I guess, on each day, and we average how many inches of rain we had overall. It's totally different from average rate of change, which is just the constant speed we would need to travel, or sorry, not constant speed, but the constant rate at which we would need for equal changes in input to correspond to the consistent changes in output. Different kind of averages. Okay, is the relationship a function? Explain. Let's take a look at the input values. We just need to think for each input, is there exactly one output? So 0, 0.9, 1, 1.1, 2, 1.1, 3, 4, 5, 6, 7, 8, 9, 10, 11. This does define a function. If we had, say, the same input with two different outputs, then it would not define a function. So for each input, there's exactly one output, and given any number of months since January 1st, there's exactly one corresponding average rainfall. It's impossible to think, well, for this month, we're going to have two different average rainfalls. Yeah, that doesn't make sense. And I accidentally put the same question twice. Let's move on to part B. Consider the number of months since January 1st with respect to the average monthly rainfall. What is the input quantity? Again, with respect to, then we have our input quantity, which is average monthly rainfall. The output quantity is the number of months since January 1st. Now, is this relationship a function? Are the number of months since January 1st a function of the average monthly rainfall? Meaning, if we know what the average monthly rainfall is, can we pick which month it was? Let's go back and look at our chart. Notice that if we consider R to be the input, there's several places where the same input appears. Like right here, 1.1 appears twice. So if I know that the rainfall was 1.1, that doesn't determine which month it was. It could be, let's see, 1 month after January, that would be February 1st. 2 months, that would be, let's see, February, March first. So February and March have the same average rainfall. So if we take as the input of our function the average monthly rainfall, we don't have just exactly one corresponding output. There's two outputs, namely 1 and 2, that would go with that input of 1.1. So we can't go backwards in this chart to make a function. So no, for some inputs, the average monthly rainfall, this is just one example. The average monthly rainfall of 1.1 inches per month, there are two corresponding outputs, 1 month after January 1st and 2 months after January 1st. So we can't say anything like f of 1.1 equals, because there's two things that we could pick. We could pick 1 or we could pick 2. That's not a function because there is not exactly one output for each input. Number 5, consider the highest recorded temperature on South Mountain with respect to the day of the year. So this is just a totally new problem context. We have some mountain and we record the temperature each day of the year. Just looking at what we have here, the temperature with respect to the day of the year, so the input quantity is the day of the year. The output quantity would be the recorded temperature on South Mountain. Now, is this relationship a function? Explain. So we have to think, for each input quantity, is there exactly one corresponding output quantity? For any day of the year, was there exactly one highest recorded temperature? Well, as long as only one person's recording the temperature, then there's going to be only one highest temperature value for the day. So we could say that this is a function. So for any given input day of the year, there is exactly one corresponding output, highest recorded temperature for the day. Number 6, consider the day of the year with respect to the highest recorded temperature on South Mountain. What is the input quantity? In this case, we're considering the day of the year as our dependent variable, or output, with respect to our input, which is the highest recorded temperature on South Mountain. Let's see, what is the output quantity? The output quantity is the day of the year. We're considering the day of the year with respect to the highest recorded temperature on South Mountain. Now, is the relationship a function? So for each highest recorded temperature on South Mountain, is there exactly one corresponding day of the year? Like, give me any highest recorded temperature, say 72 degrees. Now, if I know 72 degrees is the highest recorded temperature of the day, do I necessarily know which day it was? No. Some days, multiple days, could have had the highest temperature of 72 degrees. So this relationship does not define a function. So for each input, the highest recorded temperature on South Mountain, there is not exactly one corresponding input day of the year. The same temperature could be associated with multiple days. So the temperature does not determine which day it is. It's not a function. This goes back to independence and dependence. When you have a function, the output value depends on the input value. It determines what it is. All right, number 7, it looks like we have some, what is referred to as real math. We have a graph of a sideways parabola. So for the following graphical representation, determine if y is a function of x. Okay, so determine if y is a function of x. And it even gives us a really good hint here. Justify your answer using the definition of function. Each input value of a function corresponds to exactly one output value. So let's take a look at this graph here. We have our x-axis here. These are our inputs. And then we have Oh yeah, how did I know that was inputs? Because it says determine if y is a function of x. So x is the input and y will be the outputs. This is going to get reversed in a minute, but for now x is input, y is output. Now for each input value, is there exactly one output value? Let's just take a look at these values. Take a look at the input value 0. When x is 0, y looks to be 2.5. So for this one input value 0, there is exactly one output value 2.5. So it looks like maybe this is a function. But if we look at 1, if x is 1, what does y equal? It looks like y equals, this is about 1.8, and also when x is 1, y could equal about 3.2. So in this case, do we have, for each input value, there is exactly one output value? I hope that you thought no, because for the input value of 1, there are two output values, 1.8 and 3.2. So no, y is not a function of x. Some input values correspond to more than one output value. For example, if x equals 1, then y equals 1.8 or 3.2. You may remember back from Algebra 2 or something, this vertical line test idea, that if we draw a vertical line and the line crosses more than once, it's not a function. That will usually work as long as your input is along the x-axis and your output is along the y-axis. The vertical line test will work because you can see that for any input there would be more than one output, so it's not a function. But that won't always work, as in the next example, 8. Oh, actually, not 8, 7b. This one says, determine if x is a function of y. Justify your answer. So here, the output and inputs are switching. Now, we want to see if x is a function of y. Remember, when we say is a function of, it's always output as a function of the input. So now, y is going to be our input, and x will be the output. So let's see if this is a function. If we pick any value of y, you have to maybe tilt your head sideways and look at the y-axis. Now these are our inputs. Say we pick the value 2. If we pick y equals 2, then there is only one value of x that goes with it. Right here, we see that if y equals 2, then x equals 1/2. If y equals, say, 2.5, then x equals 0. If y equals 3, then x equals 1/2 again. If y equals 3.5, then x equals 3. Notice that anytime we pick an input, a y value, there is only one corresponding x value that goes with it. So x is a function of y. So yes, x is a function of y because for any input y value that we choose, there is exactly one corresponding output or x value. Notice here that our vertical line test doesn't help us at all, because the inputs and outputs have been swapped. Number 8. For the following graphical representation, determine if y is a function of x. Justify your answer using the definition of function. Each input value of a function is assigned to exactly one output value. Okay, so if y is a function of x, then our inputs are the x values along the x-axis here, and our output values are along the y-axis. Now we need to see if for each input value there is exactly one output value. So scanning the x-axis, scanning the inputs, looking at the function here, I don't see any input values for which there is more than one output value. For example, if we pick this input value here, 80, then here's the function value, it's 140. Notice there's only one function output. There's not more than one. So this is a function. So yes, y is a function of x because for each input x value, there is exactly one corresponding output y value. Next, determine if x is a function of y. Justify your answer. So the answer is no. Why is x not a function of y? Well, if we say x is a function of y, it means y is the input and x is the output. So y is the input, x is the output. And let's look again at this function definition. Each input value of a function is assigned to exactly one output value. I see all sorts of input values that do not correspond to exactly one output value. For instance, let's look at y equals 120. If y is 120, let's see, that occurs right here. Right here. And right here on our function. So if y is 120, well, that's our input. There's three different outputs. There's an output of x equals 20, an output of x equals about 95 or so, and an output of about x equals 180. So no, x is not a function of y, because for some inputs, there are multiple outputs. For example, if y equals 120, then x equals 20, 95, and 180. It is not the case that for each input y value, there is exactly one output x value. I hope you can see that so far in this lesson, everything that we needed to solve the task was just based on that definition. A function has to have for each input there is exactly one corresponding output. Now we're getting to the domain of a function. Recall that the domain is the set of all possible input values for which the function is defined. Remember, we did the box problem, and it didn't make sense to have a cutout length of 5 inches because it was impossible given our sheet of paper only had a width of 8.5 inches. So 5 was not in the domain of our function. Now these examples here in number 9 are more abstract, just general functions without any problem context. We just have to think in terms of numbers. Which values of the input x will give us a real output, something that's defined. Remember, there's a few things that are undefined. A function is undefined if we divide by 0. Also, we can't take a square root of a negative number. The square root of a negative number doesn't give us a real output. So those are the two big ideas I want you guys to think about when thinking about the domain. So here we have a square root. F of x equals the square root of x minus 4, and we want to find the domain. We know that we cannot take the square root of a negative number. So which inputs would work here? 5 minus 4 is 1. 1 is not a negative number. We could take the square root of 1. So x equals 5 is part of our domain. But what if we picked x equals 3? 3 minus 4 would be negative 1. The square root of negative 1 is undefined. We can't take the square root of a negative number, so that's not a possible input. Remember, the domain is the set of all possible input values for which the function is defined. In this case, what we have underneath our square root here has to be greater than or equal to 0. It can't be negative. So again, x minus 4 has to be greater than or equal to 0. Make sure that that makes sense. Then if we look at this equation, this is an equation we can solve for x to determine all the possible inputs. Let's add 4 to each side of the inequality, and then we will get this equation. Not equation, inequality. X is greater than or equal to 4. This tells us all the possible inputs, all the possible values for x are greater than or equal to 4. This is appropriate for your answer for the domain. You could also use this notation, interval notation. You could write 4 to infinity. This means the set of all numbers greater than or equal to 4. If you wanted to get a little bit more technical mathematically, you could say the set of all x such that x is an element of the real numbers. So x is a member of the real numbers, and x is greater than or equal to 4. That's called set builder notation. But any one of these three representations will work for your domain. The key from this problem is anytime you have a square root, just take what's inside the square root, set it greater than or equal to 0, and find your domain. Next, we have g of x equals 1 over x squared minus 9. Notice that we have a fraction. And it's important, remember, when thinking about the domain, to keep this in mind. We cannot divide by 0, and we cannot take the square root of a negative number. So in problem A, we were in danger because we had a square root. We had to make sure that we found the possible inputs that did not give us a negative. But here we have a fraction, and that denominator cannot be 0. Anything that makes this denominator 0 will give us an undefined value. It won't be a possible input. Again, go back to the definition of domain, the set of all possible input values for which the function is defined. Now you might look at this function and take a second to guess which values of x will work and which won't. You may have guessed 3, because 3 squared is 9, and if we subtract that 9, we'll get 0 in our denominator. That's not going to work. That's undefined. That value for x of 3 is not a possible input value. Also, negative 3 squared is also positive 9. That won't work either. Now, there's a systematic way to find the answer whenever you have a denominator and you're looking for the domain. Just take your denominator and note that it cannot equal 0. Any x value will work except the x values that make x squared minus 9 equal to 0. So let's just solve for those. Let's find out what they are. We can add that 9 to both sides of our equation. Not really an equation here, it's an inequation. But if x squared minus 9 does not equal 0, then we know that x squared cannot equal 9. You may remember that if you want to cancel a square, you take a square root. If x squared equals 9, then x has to equal the positive or negative square root of 9. Or, again, this is not equals, positive or negative 3. So x cannot equal positive or negative 3. That means our domain is all real numbers except positive and negative 3. That's a perfectly way to jot down your answer. The domain is all real numbers except 3 and negative 3. And there are some other more mathematical formalistic ways to write your answer. You could write in set builder notation the set of all x. Don't need that little square. The set of all x elements of the real numbers, so any real number x, such that x does not equal 3 or negative 3, that's another correct answer. You could also write interval notation, all the numbers from negative infinity to negative 3, but you don't include negative 3, that's why we have this open parenthesis. Then all the numbers in between negative 3 and 3, but not including 3 or negative 3, and then all the numbers from 3 to infinity. This reads the set of numbers from negative infinity to negative 3, union with negative 3 to 3, union with 3 to infinity. And we don't have brackets like we had up here with the 4. 4 was included here in our domain, but down here 3 and negative 3 are not part of our domain. Now part C, again we want the domain of the function, but if you're thinking about domain at this point of the course, all we have to think is we cannot divide by 0 and we cannot take the square root of a negative number. In this function, devoid of any problem context, h of x equals x squared plus 2x minus 5, there's no denominators, no square roots. That means that the domain is all real numbers. So all real numbers is a perfectly acceptable answer for your domain of that problem. You could also write interval notation. You could say negative infinity to infinity. That's another symbol for all real numbers. Set builder notation, you could just say the set of all x. That are elements of the real numbers. In mathematics, we often just denote that set R. It's this weird R right there. So that's the set of all real numbers. And going back to our definition, any input value would work here. The domain is the set of all possible input values. And any number we can plug into that function and get a real number output. Alright, part D. K of x equals the square root of x minus 2 divided by x minus 9. It's crucial that we go back to the definition of the domain of a function. The domain of a function is the set of all possible input values for which the function is defined. We cannot divide by 0 and we cannot take the square root of a negative number. That last part's not the definition, but it's just an awesome tip for finding the domain. Notice here we have double trouble. We have a square root. We know that x minus 2 can never be negative. And we have a fraction. That denominator can never be 0. So let's think about our possible input values. First of all, with that square root up there, we can't pick any numbers smaller than 2. If we pick 1, for example, x equal 1, 1 minus 2 is negative 1. That's less than 0. We'll have the square root of negative 1 is undefined. That just doesn't exist. So we know that our x minus 2, what's underneath that square root, has to be greater than or equal to 0. We know that. If we add 2 to both sides of this inequality, we'll obtain the inequality x is greater than or equal to 2. So that's one piece of our puzzle here. We know that all of our x values can't be smaller than 2. They have to be greater than or equal to 2. But that's not the whole story, because we also have this denominator. And you can look at that and see that x cannot equal 9, or else the denominator will be 0. The procedural way to always do this, if you want to remember a procedure, is x minus 9 does not equal 0, which means that x cannot equal 9. So that's not a possible value for an input. So let's think about what our possible values are. We said all numbers greater than or equal to 2, but now x cannot equal 9. So our domain is all the real numbers that are greater than or equal to 2 except 9. And that's one way to express your domain. All real numbers greater than or equal to 2 except 9. And there's a couple more mathematical ways that we can write out this domain. Interval notation is the best way, I think. We can start with 2 with a bracket, because 2 with that equal sign, that's included in our domain. Start with 2. We want all the numbers in between 2 and 9. We're not including 9. And then we want all the numbers greater than 9 from 9 to infinity. We put a union here in between these. So this is our domain, the set of all numbers from 2 to 9 union with the set of numbers from 9 to infinity, including 2 but not including 9. There's not a really great way to do this with set builder notation, but you could say the set of all x that are real numbers such that x is greater than or equal to 2 and x does not equal 9. Those are our possible inputs. Now, looking at part E, p of x equals x over 9. Here we have a denominator, so you might think, uh-oh, that denominator can't be 0, but look what the denominator is. It's 9. It's a constant. The denominator is always 9. We can't make that 0 no matter which value of x that we pick. So here the domain is all real numbers. You need to make sure that makes sense. There's the same problem. Let's move on to part F. Part F, s of x equals 9 over x. So here we do have to worry about the denominator being 0. Note that x cannot equal 0, because then we'd have 9 over 0. Our function would be undefined. 0 is not a possible input value. So you could say your domain is all real numbers except 0, or you could use the interval notation. This symbolizes all real numbers except 0, or you could use the set builder notation. Just the set of all x that are real numbers such that x does not equal 0. For part G, this one's pretty similar. We again have a denominator, and that denominator cannot be 0. And you can see what would make it 0 would be 5. X cannot equal 5. So you could say your domain is all real numbers except 5, or you could use the interval notation, negative infinity to 5, union with 5 to infinity, not including 5. And last but not least, m of x equals square root of 2 minus 3x. Again, we have a square root. We know that it can't be negative. So what's inside that square root, this 2 minus 3x, this is just going to be a number. We just take some number x, multiply it by 3, subtract that from 2. We know that that resulting number has to be positive. It can't be negative. If we solve this inequality for x, say by adding the 3x to both sides, There's more ways than one to do this. But then dividing by 3. We see that 2/3 is greater than or equal to x. The better way to look at that is x is less than or equal to 2/3. Meaning our domain is all the real numbers less than or equal to 2/3. Here's the interval notation. So I hope that you noticed in this lesson that everything boils down to our definitions. If we really understand the concepts behind those definitions, then we can solve pretty much any problem.